So here students, for today we'll see what do we mean by voltage regulators. So on the same lines, we'll have a topic as voltage regulator. So the topic for the day will be voltage regulation or voltage regulator. Okay. And in this, the main device which is going to work or which is going to give you this application of voltage regulation will be a component which you have studied as Zener diode. Voltage regulation means what? Okay, now whatever input you are going to get from your supply, the main supply, say this is your voltage regulator. Okay, so we'll just draw this is black box, you can say. This is your voltage regulator. And now the aim of this regulator is to keep the output voltage, whatever it gives here, it has to keep the output voltage constant. Okay. The output voltage constant means what? Whatever input you give here from your main supply, whatever input you are going to give here, even if the input goes above a certain specific value, in that case, the output should not go above a specific value. It should remain to that specific value. So we say the output remains constant in spite of variations in the input. And even if the load, whatever load you are having for your application, even if this load changes, varies, okay, then also there can be a problem in your output. So then the current which is given to the load, if the load is becoming more, it will draw more current. Okay, so in that case also the output should remain in a stabilized way. Output should remain constant. Okay, so that is how a voltage regulator is going to work. Now, as a whole, if you see the definition, voltage regulation means even if the input is going to vary above a certain limit, or even if the output load is going to vary above a certain limit, in spite of that, in spite of both these variations, the output voltage which is given to your equipment, which is given to your appliance, should be constant, should remain constant. There comes the concept of voltage regulation. Okay. And now here we are going to build our voltage regulation with a component which you have studied named as Zener diode. Zener diode. So if you can remember, we had studied this when we studied active components, and the symbol for that was something like this. This was little bend here. This was little bend. So this was Z. What you can see, Zener diode. Okay, so this is anode, this is cathode. So this component we are going to use and build a regulator. Okay. So at this point, did you understand means what is this voltage regulation? Voltage, yeah. Now this voltage regulation becomes very important because in electronics, whatever appliances we built, okay. Now most of the times you must have seen your most of the ICs, your gates, or digital logic gates where you have studied AND gate, NOR gate, NAND gate, and all. All these ICs work on how much voltage? Only 5 volts. The VCC supply will be only 5 volt. Okay. The supply which you get from the electric pole to your house or to your labs, and then from your main supply, it's around 230 volts. And that 230 volts first should be brought down by a transformer, and then it should be rectified to DC. AC should be converted to DC, and that particular DC will be used for the applications. And every electronic circuit, whichever is there in the appliances, whatever you use in your house, will require this specific amount of voltage, either 5 volt or 10 volt. It will be in lesser valuable. The voltage requirement will be less only in electrons. So we are not working with a circuit which requires 230 volts. We are not working with a circuit which requires 440 volts. Those type of circuits are dealt with electrical engineers. But when it comes back to electronics appliances, electronic circuits and all, the circuits require a lesser voltage, and that voltage should remain constant. The supply given to a particular circuit should remain constant. It should not vary. Otherwise, the behavior of the components which are there in your circuit will malfunction. Means the behavior will not be correct, and then you might get wrong results. So the supply what you give to your circuit is very important. Now here voltage regulation concept comes in the power supply part, the power supply which you give to your circuits. Okay. Now this is your introduction for voltage regulator. Then we will one by one see what is Zener diode, and then we will build up a voltage regulator circuit with that, and we'll see what are the types of regulations you get and how does a Zener diode work as a voltage regulator. Okay, all this theory is important. See, once you come to the lab, then only you're going to take Zener diode, you're going to connect it in a reverse bias condition, and you're going to show that the current will be increasing and voltage will remain constant. Only that much you're going to show. But what is that used for? It's very important. Okay. So here, let's start with the contents of this or today's class. So first, you will be seeing what is the concept of voltage regulation. Means what is exactly voltage regulation, as I've told you earlier now. Then why do we need voltage regulation? Then Zener diode as voltage regulator. Then you're going to use a component like Zener diode, which will work as voltage regulator. Then working of voltage regulator circuit, which is built up with Zener diode. Then a condition of regulation, then types of regulations. Okay, so here importantly you're going to study Zener diode as voltage regulator. Okay, so before that we should know what is voltage regulation, as I've told you earlier. So we'll start with that. So voltage regulator, so here you can see the definition. Voltage regulator is a device that maintains a constant DC output voltage irrespective of changes in the input voltage or load conditions. So even if the input voltage, this is your input voltage, which is the input AC, whatever you supply from the mains input, even if this varies, or the load is your output resistance, which is drawing the current, even if that varies, in spite of both these variations of the input or variations of the output load, you have to maintain a constant DC output voltage. This is very important definition of voltage regulation. So voltage regulator is a circuit, or it is a device that maintains a constant DC output voltage in spite of changes in input voltage or in spite of changes in load conditions. Okay, so with that you are going to have your output voltage which will remain constant. Then we'll see what do you mean by Zener diode. Then Zener diode is a special kind of diode. Okay, now why we are calling it a special kind of diode? Because it allows current to flow in the forward direction as normal diode. That means when you are speaking about forward bias and reverse bias condition, what we have studied earlier, it will allow forward direction. That is, whenever it is forward biased, it works as a normal PN junction diode only. So if you remember what was forward bias and reverse bias, and we have seen graphs for that also. So this was forward bias. So when you say it is forward biased, you can show the diode like this, and it will be connected to positive terminal, and negative terminal will be connected to cathode. So positive will be connected to anode. This is will be cathode. Okay. Now, if you speak about a conventional PN junction diode, or if you speak about Zener diode, if you want to speak about Zener diode, then make this symbol like this. Okay. That means in forward bias, whatever forward bias you are applying here, okay, voltage. In forward bias, it is going to behave as a normal PN junction diode only. That means it's graph. If you see, whenever you draw the graph, the x-axis will be voltage, This will be the forward voltage, and this will be the forward current. Y-axis will be the current, and the graph will be shown like this. Okay, so here you can have something called as your knee voltage, 0 to knee voltage, and that knee voltage has to overcome, the potential barrier has to overcome, and after that you see even if you increase the voltage a little, there is a increase in current, and this is your forward bias condition. This is your forward bias condition. This is what we have seen in the diode. Now, Zener diode is a special kind of diode which permits the current to flow in forward direction as normal. Okay, it is working as a normal diode in forward bias condition, but it is having a very important feature when it is reverse biased. Okay, now how do you see reverse bias condition looks like? So here, if you see, you can have a diode. Okay, now this diode, we'll take it as Zener diode only. So we'll draw a Zener diode symbol, and here you can apply the voltage such that the negative terminal of the battery is connected to the anode and positive terminal of the battery is connected to the cathode. So this is your reverse bias condition. So minus plus, okay, this is the reverse bias voltage what you are applying. And if you draw the graph for it, okay, so you can see that if your x-axis is voltage, then it is negative voltage here, and if your y-axis is current, so it is negative current, and we are drawing the graph in the third quadrant. And for normal diode, this will be a breakdown here which will look like this. Will be for a normal diode, but for Zener diode, if you see this graph, okay, this graph, so this is your voltage and this is your current. Okay, if you see this graph, initially there will be no current flowing, and then suddenly when there is a breakdown, there is a sharp breakdown. There is a sharp breakdown at the breakdown voltage. At the breakdown voltage. This is your breakdown voltage for normal diode. This is for Zener diode. So this is for normal diode. This is for Zener diode. Okay. In normal diode, you can have breakdown which is called as avalanche breakdown, and for Zener diode, you can have a breakdown which is called as Zener breakdown. Okay. Now here, the importance of this is, if you see this increase in current in reverse bias condition, this part is very important. You are having the voltage, that is the breakdown voltage here, as constant voltage, but the current can vary from one point to another within certain limits. So this variation in the Zener current for a constant voltage, means for a fixed voltage, whatever is specified by the manufacturer, for a fixed voltage, whether it is 6 volt or 12 volt or any other value, for a fixed breakdown voltage, for a fixed reverse voltage, whatever you are applying, at that time, the current which is flowing through the Zener diode, because of Zener breakdown, because this will take place after a certain reverse voltage is applied, that current will vary within certain limits, keeping the voltage constant. Keeping the voltage constant. This is a very important feature of Zener diode, which makes it a very important component for application like voltage regulation. So here you can see the definition. After that, after normal, you can see that, but will also allow it to flow in the reverse direction when the voltage is above the breakdown voltage or Zener voltage. This is an important feature. This is an important part of the definition of Zener diode. Okay. Now, what it is exactly, we will see when we go to see the circuit. Okay. So this characteristics of Zener diode in reverse bias condition is very important, and that too whenever the applied voltage will just cross the breakdown voltage. At that time, the voltage will remain constant and current will go on increasing if you increase the voltage. So that feature, that sharp breakdown feature, where the voltage is going to remain constant at a particular value, gives you a chance to build a voltage regulation application using this type of component, which is called as Zener diode. So next, you can see here another way I have shown you. The Zener diode appears like this. So this is how we have earlier also seen appearance of Zener diode. Okay, so you can see this strip. You can see this strip So the terminal near the strip will be called as cathode, and the terminal away from the strip will be called as anode. So this is your positive and this is your negative terminals. And even if you see the symbol will be same like your conventional diode. Only thing here, the bar will be having. So the bar is bended, you see. It is bend on top and bend down. So here, this can be taken as anode, this can be taken as anode, and this can be taken as cathode. Okay, these are the two terminals of the diode. And then the most important feature I've shown with this arrow here, backward current flows too. This is the reverse current. Okay, but only when it passes the voltage applied passes Zener breakdown voltage. That is what we have seen in the graph. When the applied voltage is going to be, this is the voltage, applied voltage across the diode. This is the current. Initially, when you start from zero, when you increase the voltage, there is no current through the diode, but suddenly once you reach this breakdown voltage, which is called as Zener voltage, there will be a large increase in current and voltage remains constant. So this part is your Zener breakdown, and this will be used in certain limits. You will not allow the diode to get damaged, but then this is the area which helps you to make a voltage regulator. Then we will see how do we build up a circuit of Zener diode as voltage regulator. Now we know the basic condition now to use Zener diode as voltage regulator is it should be connected in reverse bias condition. Okay. Now here, if you draw your Zener diode like this, here you can see this is your Zener diode. So if you draw it like this, then where is the anode? Anode is down and cathode is on top. Okay. Now cathode will be connected to positive terminal of the battery. Here you can see the input positive is connected to the cathode and the input negative is connected to anode. So this combination says that your Zener diode is connected in reverse bias condition. This is very important. And then we have a resistor R here, a protective resistor. This will be resistor R. Then whatever input you're going to give, because of that, the current which arises is taken as the source current IS. And then you see here, across the Zener diode, you are having this load of your application also. Then the current which flows in this branch, Zener diode branch, is called as Zener current IZ, and the current which is going to flow through the load is the load current IL. And here you have relation of this current, that is the source current will be equal to Zener current plus load current. Okay, now this is a very important relation to have when you explain the working of Zener diode as voltage regulator. Okay, now here you can see the circuit, means you can introspect the circuit. You can see that the Zener diode is connected in reverse bias condition and there is an input supply voltage applied which is called as Vs. So here you are going to apply your input voltage Vs, and that Vs will make a current flow which is called as Is. Is will flow through the diode also and through the resistance also at the output, which is load resistance, and the voltage across that load resistance will be our output voltage. So here, according to my definition of voltage regulator, I want output voltage to remain constant in spite of variations in the input voltage or in spite of variations in the load resistance. This I want to show. Okay. So then we will take a circuit of Zener diode in this way only, and then we will explain that. Okay. So you can see this circuit. Now in this circuit, I have made a little change. I have changed the position of the Zener diode. So here you can see the Zener diode is connected here, and here you can see you are having anode and this is cathode. Now for Zener diode to be in reverse bias condition, anode should be connected to negative terminal of the input. So this is your input voltage This is your input voltage. And in this input voltage, we have shown negative point on top and positive polarity down. So anode is connected to this negative polarity and cathode is connected to positive polarity. That means Zener diode is reverse biased. Okay, same thing as we have seen in the earlier circuit. And here you will be having a protective resistor R, and here you can show the directions of the current. Now because we have inverted the position of the zener, you can show that this is your main current I, which can also be called as IS, source current. This will be your load current IL, and this will be your zener current IZ. And here also you see that current I or IS, whatever you take, will be equal to zener current plus load current. Okay, and here you have your load resistance RL, and the voltage taken across load resistance means whenever you have resistance, whatever current flows through that resistance, current multiplied by that resistance will give you the voltage. So here you are having this as output voltage. E naught will be your output voltage. Now here the Zener diode should be explained as how it is going to behave as voltage regulator. Okay, now you have to take two conditions when you are explaining that. And the two conditions says that in the first condition, you should tell when the input varies, input goes above the Zener voltage. If the input varies and the output load remains constant, input is going to go above the specific value of Zener voltage, reverse breakdown voltage, and the output load is going to remain constant. At that stage, the output voltage should remain constant. And the second condition will be input voltage will remain constant, but there will be a variation in the output load. This RL is going to vary and it will draw a varying current. The load current also will vary. In that case, the Zener current should adjust and see that the output voltage remains constant. So in both the cases, whether your input is going to vary or whether your output voltage is going to vary, in both the cases, your output voltage has to remain constant. This is what is expected with this voltage regulator circuit, which is built up of Zener diode. Okay, then we'll go to see the theory of it. So here, one more circuit I've shown. The same Zener diode is been converted into a battery here, and you can see this is the voltage across the Zener diode, which is called as VZ. And the same circuit, it is connected in reverse bias condition, and Zener diode, that is voltage across the Zener diode, is VZ. Okay, and this is the applied voltage and this is the output voltage. So here, when the circuit is properly designed, the load voltage E naught, that is the output voltage, remains essentially constant, that is equal to VZ, that is Zener voltage, even though the input voltage EI and load resistance RL may vary over a wide range. That means you are operating in an area where you see the reverse bias graph of Zener diode. You are operating in an area when the reverse voltage comes and reaches the value of Zener breakdown. Reverse voltage comes and reaches the value of Zener breakdown, and then there is a sharp current here. So this is your Zener voltage VZ, and this is the area what we are speaking where the current is increase or decrease. You are having a variable current here at a constant voltage value, and that is the area what we are going to use of Zener diode for this voltage regulation application. Okay, so even if the input voltage EI varies, or even if the load resistance RL vary, the output voltage E naught should remain constant in the circuit what we shown earlier. So here we'll take the first case. Suppose the input voltage increases. Since the Zener is in the breakdown region, the Zener diode is equivalent to a battery as shown in earlier figure. It is clear that the output voltage remains constant, that is Vz is equal to E naught. The excess voltage is dropped across the series resistance. This will cause an increase in the value of the total current I. The Zener will conduct the increase of current in I while the load current remains constant. Hence, output voltage E naught remains constant. irrespective of the changes in the input voltage EI. So what does this mean? So what does this mean is, if you increase this input voltage, this is your input voltage. If you increase this input voltage, okay, it is increasing, and say it has reached your Zener voltage, that is the breakdown voltage, and above that if you're increasing, okay, above that if you're increasing. Now here the load RL will remain constant, it is not going to vary, but you have increased the input voltage. So what will increase is your input current will increase. Okay, the input current will increase, and we know that the relation of input current I is equal to IZ, that is Zener current plus load current IL, plus load current IL. Okay, when input voltage increases, the main current will increase. Okay, now, I don't want here that the load current should increase. Okay, we don't want load current to increase, because load current into load resistance will give you the output voltage, and we don't want output voltage to vary. We want output voltage to be constant. So what will happen is, when the input current increases, the load current will remain same. The load current will remain same, but who will help him is the Zener current. Zener current will increase and take the extra current through the Zener diode when the load current is increasing, and it will see that the output current through the load remains constant, so that that current multiplied by output resistance, that means output voltage here E naught, output voltage will remain constant. This is what is the meaning for that. And who is helping here? The Zener diode is helping here, because it is allowing more current to flow through Zener itself, because we know that when it is reverse bias, you are having this condition here. This is the important condition where you can keep the current constant at a particular voltage. Okay, so that is what is the feature. So that is what the meaning. And this type of regulation is called as line regulation, because here the input is going to vary, the load is going to remain constant, but the output voltage, because of Zener diode, is going to remain constant. Okay, so this is called as line regulation. Similarly, we will see the second point. Second point says that, now suppose that input voltage remains constant, but the load resistance RL decreases. Load resistance decreases. This will cause an increase in load current, IL. The extra current cannot come from the source because drop in resistance, and hence source current I will not change as the Zener within its regulating range. The additional load current will come from decrease in the Zener current, and consequently the output voltage remains constant. Now this is the second point which tells you the concept of load regulation. So how does this? So here we say that the input voltage will remain constant. So this voltage, input voltage here in the second case, is going to remain constant, and this load resistance is going to decrease, and when it is decreasing, it will see that the current flowing through it, that is a load current, increases, because you are having a relationship of resistance and current inverse according to Ohm's law. So if resistance decreases, this current increases. And here we have a thing that the input voltage is constant. That means our main current is constant. So if you take the relationship I is equal to IZ plus IL, so this is not varying, this is constant. This is increasing, load current is increasing because your load is decreasing. Then who has to compensate with that? Then the Zener current will decrease. Zener current will decrease. So Zener current, that is IZ, which is flowing through the Zener diode, because it is in reverse bias condition. So here you can see you can decrease the Zener current also, or you can increase the Zener current also. Okay, so here Zener current will compensate and will see that the load current increases, and then that value of load current increased with a decreased value of load resistance R will give you again a constant output voltage at the output. So this will be the second case of the working, which will support the concept of load regulation. So this is the second point what we saw in the circuit. So voltage drop across R, that is the initial resistor, is EI minus E naught, that is the input voltage minus output voltage. So current through R, I is equal to IZ plus IL, what we have seen, and applying Ohm's law, we can have the value of R. R will be equal to EI minus E naught, that is input voltage minus output voltage upon Zener current plus load current. This is equation what you can get from the circuit. Then what is the a condition when we say zero voltage regulation? So here a condition for zero voltage regulation means, okay, sending end voltage, sending end voltage and receiving voltage becomes equal. When the voltage what you have sent from the input to the output and the voltage at the output, both if they're equal, this case is known as the ideal voltage regulation. Ideal voltage regulation is desirable in a power system but not possible practically. This is the condition for zero voltage regulation. Similarly, we'll see one more condition, a condition for maximum voltage regulation. Maximum voltage regulation means the difference between the receiving voltage, that is the output voltage, and the sending voltage. So the difference between the receiving end voltage and the sending end becomes very large. Then it will be called as maximum voltage regulation. Okay. Then again, we'll go to see types of regulators. Now, regulations type or regulators type can be classified in different categories depending upon their working and also depending upon their connection. So first, depending upon their working, we will see what are the types. So, or depending upon the type of regulation that is working, the regulators are mainly divided into two types, namely line regulator and load regulator. Now, this we have seen in the working of Zener diode as voltage regulator. We have seen line regulator. Line regulation will come into picture when the input varies above a specific value. The output load is not going to vary, but the output voltage will remain constant. And in load regulator, what will happen? The input will remain constant. The output load is going to vary, but still the output voltage will remain constant. Okay, so that is line regulation and load regulation. So here, if you have a definition for line regulation, you can say that in this type of regulation, series resistance and load resistance are fixed. Only input voltage is changing. Output voltage remains the same as long as the input voltage is maintained above a minimum value. This is the definition for line regulation. Similarly, if you see the definition for load regulation, in this type of regulation, input voltage is fixed and the load resistance is varying. Output voltage remains same as long as the load resistance is maintained above a minimum value. This is the definition for load regulation. Now, depending upon the connection of the voltage regulators with the load, okay, there are two types of voltage regulator. One is called as series voltage regulator and the other one is called as shunt voltage regulator. So here you can see the first figure what I've shown is a series voltage regulator, because here the voltage regulator circuit is in series with the load, okay. And in the second figure we have shunt voltage regulator, that is parallel voltage regulator, because here the voltage regulator circuit is parallel with the load. So it is parallel with the load. Okay, so if you're having the voltage regulator circuit in series with the load, it is called a series voltage regulator as this. And if you're having the circuit in parallel with the load, voltage regulator circuit, if it is in parallel with the load, then it is called as shunt voltage regulator. So these are again two types of voltage regulators. Clear? So I think with this, we have finished this concept of voltage regulation. Thank you, students.